All right, so here we are for the next part of our amino acid analysis and our discussion of amino acids. Now, if you look at the table off to, I guess that would be the left of the screen, you've got a list of every single amino acid, and you've got their pKCs or pKa for their C termini, pKa for the N termini, and then their pKa for their R groups. Now, of the amino acids that we already kind of talked about with ionizable R groups, we talked about those that were positively charged at a neutral pH, 10.5 for lysine, arginine, and histidine, which have pKa's of 10.5, 12.5, and 6.0. The other amino acids, aspartate and glutamate, they're going to have pKa's for their R groups at 4.9 and 3.1. So those pKa's, these are our negatively charged residues, and these other ones are our positively charged residues. The negatively charged residues are deprotonated at a physiological pH or a neutral pH, and the positively charged residues are positively charged at a physiological pH. Now this last column right here is the pi, which is also known as the isoelectric point. This is the point at which the molecule has no net charge or a net charge of 0, and it's the point where the molecule is least soluble. Okay, so if you think about like an insoluble salt, an insoluble ionic compound, that's something like if you put sand, silicon dioxide, into a glass of water, well, sand is insoluble, so it's going to precipitate out. It's going to be a solid at the bottom of the container. Proteins do the same thing. They become insoluble, and therefore you need to, figure out the conditions to precipitate them. So there are insoluble ionic compounds that will solubilize under the right conditions. Okay, so that's basically the rundown of this table. Now we're going to work with it for a little bit. So one thing that's commonly done is titration of amino acids. Amino acids contain at least 2 ionizable groups. The predominant ionic form of that molecule depends on the pH of that solution. Now, titration can be used to predict the reactivity of amino acid side chains. All amino acids, peptides, and proteins have an isoelectric point, which I already introduced. And that's the point where the molecule has no net charge. How this is calculated for a diprotic amino acid is, well, you take the 2 pKa values, divide it by 2. And you know what? For titrating or for calculating the pi of a triprotic amino acid, you take 2 pKa values, you divide it by 2. The important part between a triprotic and a diprotic amino acid is that a triprotic amino acid, you've got 3 pKa's. So you've got to select the right pKa's. And I'm going to show you how to do that in just a moment. So first, let's go with a diprotic amino acid. Calculate the pi for amino acids with an R group that cannot be ionized. Well, that would be pKaC and pKaN. The only 2 groups that have pKa's that, well, or the only 2 ionizable groups, the only 2 pKa's on that molecule. So for something like alanine, you would take 2.4, 9.9, add them up, divide by 2. And you'd end up with something like this. 2.4 plus 9.9 divided by 2 is 6.15. So if you got alanine and adjusted it to if you got alanine and put it in a solution with a pH of 6.15, 100% of the alanine in that solution would have no charge whatsoever. And that molecule would be least soluble at that pH. Okay, now let's calculate the pi for an amino acid with an R group that contains a carboxylic acid. So this would be glutamate or glutamic acid. Now, like I said earlier, the way that it's displayed here as an ion, that name is correct. If this were protonated, that would be glutamic acid. But for this purpose, we don't really worry about that too much. Now, the way that I always like to figure this out is I always like to look at my groups. And I'll say, okay, what are my pKa values? Now, my head is thankfully hiding these, but I have ways of navigating around this. And I can say, well, my pKa for glutamate is 2.1. Then I've got, let's see, my next group is 9.5 and 4.1. 9.5 and 4.1. What I like to do is I like to imagine this molecule being drawn at a pH of 1. lowest possible pH. So I'm going to protonate everything. So this molecule is going to have a charge of +1. Okay. Now, whenever I add a strong base, what's going to happen is my first group, my lowest pKa, right here, is going to be deprotonated. Okay. So whenever I've adjusted the pH of my solution to 2.1 or above, above 2.1, that group has been deprotonated. So I've got a negative charge there. So I've got a negative charge on the C termini and then a positive charge on the N termini. Have I done anything to the R group? I have not. So that means this group and this group cancel one another out effectively, and this group right here has no charge whatsoever. Now, what does that mean in terms of, well, how do I calculate my PI? My PI is specifically over 2 pKa values. Where is it that 100% of my molecule has a charge of 0? Well, I know that my molecule will transition from a +1 to a 0 charge, and then as I continue to deprotonate it and as I continue to add base, now all of a sudden I've got 2 groups with negative charges. So that means my molecule will have a -1 charge. The way that I like to do this is I like to add up determine my charge range. So this molecule will go from a +1 charge to a 0 to a -1, and then ultimately once this group right here is deprotonated, it's going to be a -2 charge. After that, what I like to do is take my pKa's and list them in sequence from lowest to highest. And I'll say 2.1, 4.1. Those 2 pKa's that I've indicated right here, 2.1 and 4.1, they give me my range from +1 to 0 and 0 to -1. So I can use those 2 values as my charges, or as my pKa's. So I'll say 2.1 plus 4.1. Divided by 2, that would be 6.2. Divided by 2 is 3.1. And that's all there is to it. Now I'm going to do the exact same thing using lysine. So I'm going to draw lysine at its lowest possible pH when every group is protonated. There we go. I've got a +1 up here on the N termini. I've got a +1 on the R group, and no charge on the C termini. So that means my molecule can be +2. Now, as I deprotonate it, my C termini is going to be the first group to fall. And that's going to mean that my molecule is going to transition from a +2 charge to a +1 charge. My next group is going to be my N termini, which has a pKa of 9.1. And that's going to transition from a +1 charge to a 0 charge. And then the last group is going to be pKa of 10.5, where it's going to transition my molecule from +1 charge to a 0 to a -1. So my molecule has a total of 3 pKa's. I'm going to list them in my sequence: 2.2, 9.1, and 10.5. So I've got my charge range. This molecule can be at one extreme a +2 charge, and at the opposite extreme a -1 charge. Now what I want to do is, since I've listed out my charges from the lowest possible pH to the highest possible pH, I want to apply these pKa's to these arrows right here. So the only charges, what I care about when it comes to PI calculation is what are my pKa's that give me a transition from +1 to 0 and a 0 to a -1. 9.1, 10.5. Your PI calculation, therefore, is going to be 9.1 plus 10.5 divided by 2, or that would be 19.6 divided by 2 equals 9.8. So my PI, for an amino acid like lysine is going to be 9.8. So what's important, and the way that I like to do this is I like to look at what can my molecule's charges be. I like to put it at a lowest possible pH and then kind of walk through the sequence and see what is the charge at its highest possible pH. And that's how we end up with the way that we did it right here. Okay, so a titration curve for something like glutamic acid is going to look like this. It's got a total of 3 pKa values. They're displayed right here. The first 2 pKa's, they're going to be very close together with one another. Your PI, or your isoelectric point, is going to be between those first 2 pKa's. The important part about this is all about the charges. So plus, let me switch to red again. +1, 0, -1. Those are my 2 pKa's that I care about. Now, the pKa and the PI calculation for something that would be like alanine, for instance, well, your titration curve is going to look a little bit different, but the same principles are going to assign. You've got your cationic form and your anionic form of the molecule. Those are your extremes. This is a diprotic amino acid. Now, this term in the middle right here is something that's also worth noting. It's the zwitterion, and this is a term associated with a molecule that can have simultaneously a positive and a negative charge on the same molecule. Amino acids are capable of being zwitterionic for this reason. So, what you do with the alanine titration curve is, well, here's your first pKa, here's your second pKa, and there's the PI right in the middle between the two. So, due to their nature, amino acids can undergo numerous chemical modifications. The first of which is a peptide bond can form between them. So, those N and C termini of adjacent amino acids can form a peptide. Likewise, cysteine, which is one of the 2 amino acids with a sulfur in it, but cysteine has what's known as a sulfhydryl group. Cysteine can be oxidized to form what's known as a disulfide bond. So 2 adjacent cysteine or 2 nearby cysteine residues can basically form a covalent bond between the 2 of them. Now that's an important thing because that's a covalent bond. That's a very strong bond. So those are going to be basically held together. Now, proteins are the entities that are built up from amino acids, and they can have a ton of different shapes. Likewise, they can be multiple peptides, or they can just be a single peptide. So most tasks performed by living cells require proteins. They perform a variety of functions. They also provide structural stability, or provide a structural role or play a structural role. They're involved in metabolic regulation, movement of molecules, defense, as well as catalysis, so catalyzing specific reactions. Biologically active amino acids, in addition to their role as building blocks of proteins, amino acids have several other biological roles. Several amino acids are derivatives or used as derivatives for making neurotransmitters. For instance, L-DOPA is derived from tryptophan. They're also precursors of complex nitrogen-containing molecules. So nitrogenous bases of your nucleotides are also derived from amino acids. And heme, which is the ring structure that holds in its center an iron atom, which hemoglobin utilizes, that's all derived from the amino acid glycine. I believe it was glycine. We'll get to that later on this semester. But they're also metabolic intermediates, and so they provide a number of different roles beyond just kind of building blocks of proteins. So biologically active amino acids, I mentioned this a little while ago, just a moment ago. Tryptophan here is utilized through a series of steps to make melatonin. I think I said L-DOPA, but that was incorrect. It's melatonin. So there you've got that right there, our tryptophan residue. Serotonin is in the middle of that. And then the final step, you're going to produce melatonin. which my children do not believe can slow them down because they do not sleep. Amino acids are also precursors for nitrogen-containing molecules. Glutamate, it goes through a series of steps and ultimately is used to produce heme. I said glycine. I apologize for that. It's glutamate. And then amino acids act as metabolic intermediates. And I'm blocking this right now. I apologize for that. But this is in the urea cycle. Arginine amino acid is involved in the urea cycle in order to remove nitrogenous waste. And we'll get into that later on in the summer session. Later on, I believe that's in chapter 3 material, or exam 3 material. We'll get to that later on. In the meantime, we proceed.